Hello, and welcome to this complete guide on loop diagrams. If you are an instrumentation engineer, a designer, technician, or student, especially one focused on the oil and gas industry, this presentation is for you. Loop diagrams are one of the most fundamental and critical documents in instrumentation design engineering. They act as the essential bridge, connecting the high-level concepts you see on a P&ID to the detailed real-world wiring required for installation, commissioning, and maintenance. Over the next few minutes, we will cover this topic from start to finish. We'll explore what a loop diagram is, why it's so important, what elements it contains, and the standards that govern its creation. We will also walk through the step-by-step procedure for preparing one, look at common mistakes, and discuss its vital role during plant commissioning. Let's get started. So, what exactly is a loop diagram? At its core, a loop diagram is a schematic representation that shows the complete interconnection of all the components in a single instrumentation loop. This isn't a high-level overview, it is a granular, detailed drawing. It provides a complete view of the wiring, signals, and configuration for each specific loop. But why is this so important? Loop diagrams are absolutely critical for project documentation and commissioning. They are the primary communication tool used between the design engineers, the construction crews who install the devices, and the commissioning teams who bring the plant to life. When a technician is in the field needing to verify a connection or troubleshoot a problem, the loop diagram is the essential document they use. It is indispensable for ensuring proper installation, for systematic loop checking, and for all future maintenance activities. Let's dive a bit deeper into the specific purpose of these diagrams. As we mentioned, their first key role is to facilitate clear communication and coordination between the various teams involved in a project. The design team creates it, the construction team builds from it, and the commissioning team verifies against it. The loop diagram ensures everyone is on the same page. Their second major purpose is tracking. A loop diagram provides a comprehensive, end-to-end view of the entire instrument loop. This allows an engineer or technician to easily trace a signal's path, from its origin at the field sensor, through every junction box and terminal, all the way to the specific I/O channel in the control system. It also serves as the master document for calibration details and specific wiring information, such as cable tags and wire colors. In short, these diagrams play a crucial role in documentation and communication throughout the project. Now, let's look at the basic elements you will find in almost every instrument loop. First, you have the field instruments. These are your eyes and ears in the process. The sensors, transmitters, and control valves located out in the plant to measure and control process parameters. The wiring from these devices typically runs to junction boxes, which are rugged electrical enclosures used in the field to connect and terminate instrument wiring. From these junction boxes, multi-core cables run back to a central location, often to marshalling panels. These are centralized panels that consolidate signals from many loops before distributing them to the control system. Finally, the signals land on the DCS or PLC I/O, the input-output modules in the distributed control system or programmable logic controller. These are the brains of the operation that interface with the field instruments. Of course, these loops can be traditional 4 to 20 milliamp analog loops or modern digital loops using field bus protocols. Here we see the typical architecture of a loop diagram using the furnace temperature control loop as an example. This provides a clear overview diagram showing the connection from the field transmitter all the way to the DCS. Let's trace the signal flow. On the far left, in the process area, we have the temperature element, TE205, connected to the temperature transmitter, TT205. The signal, represented by the dashed line, leaves the transmitter and goes to a specific terminal strip, TB15, in the field junction box, JB12. From there, it's carried via cable 3 to the control room panel, CP1. It lands on another terminal strip, TB11, and finally connects to the specific input terminals, 21 and 22, of the temperature indicating controller, TIT205. A key feature is the clear indication of signal flow, showing how the information moves from the field to the controller. Based on opinion, They are governed by strict industry standards to ensure consistency, clarity, and safety. The most important standard is ISA 5.4, which is dedicated specifically to instrument loop diagrams. It defines the standard methods for creating and interpreting them. Closely related is ISA 5.1, which covers instrumentation symbols and identification. This is essentially the dictionary for our diagrams. It defines what every symbol for every instrument and signal line means. For loops that are part of a safety system, IEC 61511 on functional safety is paramount. This is the international standard for safety instrumented systems in the process industry. Finally, on any real-world project, you will also have company standards. Major oil and gas companies like Shell, Aramco, and others will have their own specific requirements that build upon and add detail to the base ISA standards. To prepare an accurate loop diagram, an engineer must first gather several key input documents. You can't start drawing in isolation. First and foremost is the P&ID, or Piping and Instrumentation Diagram. This shows the process flow and identifies the instruments in the loop and how they relate to the process. Next, you need the instrument index, which is a master database or list of all instruments in the project, along with their tag numbers and specifications. The I/O list is also essential, as this maps each instrument to its specific DCS or PLC channel. Then, you need the detailed wiring details, which include cable schedules, junction box termination drawings, and cable routing information. You'll also need the instrument datasheets for technical specs, and finally, the control system architecture diagrams to understand the overall system topology. In modern engineering, we use specialized software to create and manage these complex documents. While simple diagrams can be drawn in AutoCAD, which is a widely used general CAD software, large-scale projects rely on database-driven tools. The industry standard for many years has been SPI, or Smart Plant Instrumentation. This is a specialized software built specifically for instrumentation design. Other major players include Aviava Instrumentation, which is part of a larger plant design suite. These are known as data-centric tools. This means the loop diagram isn't just a static drawing, it's a visual report generated from a central database. When you update the instrument index or I/O list, the loop diagrams can be revised automatically. This is far more efficient and dramatically reduces errors. Other tools like ePlan are also used, particularly for detailed electrical CAD and control system design. A critical concept for any project is the loop numbering philosophy. This is the standardized logical system used to identify every single instrument loop in the plant. A good tag numbering format is descriptive and consistent. It typically embeds key information such as the plant area, the service or parameter being measured, and the instrument type. For example, a common convention is a format like AABBBCCCC. Here, AA might be the plant area, like Unit 10. BBB could be the service code, like FT for flow transmitter. And CCCC would be the unique loop number, like 101. So, a tag like 10FT1001 instantly tells an operator or technician its location and function. This consistent philosophy is crucial for effective communication, documentation, and maintenance throughout the plant's entire life cycle. Loop diagrams must also clearly represent the type of signal being transmitted, using standard symbols. The most common is the 4 to 20 mA analog signal, a robust standard used for decades to represent a process variable. You will also see the HARP protocol. This is a hybrid signal that superimposes digital communication on top of the 4 to 20 mA analog signal, allowing for additional data like diagnostics and configuration. We also have simple digital signals, which are basic on-off or open-close status signals from switches. Pulse signals are discrete signals often used for flow meters or speed measurements. And finally, we still use pneumatic signals, which are air pressure signals, most commonly used for the actuation and control of control valves. Each of these will have a unique line symbol on the diagram. So how do you actually prepare one of these diagrams? Here is a reliable step-by-step procedure. First, obtain project documentation. Gather all the inputs we discussed, the P&ID, instrument index, I/O list, wiring details, and datasheets. Second, understand the control system architecture. Review the diagrams to know the DCS PLC I/O layout. Third, assign loop numbers based on the project's established numbering philosophy. Fourth, create the loop diagram, visually representing all the elements from the field instrument to the control system I/O. Fifth, indicate signal types and symbols using the standard ISA symbols for analog, digital, or other signals. Sixth, specify wiring and terminal details. This is critical. You must document every terminal number, cable core color, shield, and ground point. Finally, review and verify the diagram. You must cross-check your completed loop diagram against the PNID, index, and cable schedule to ensure it is 100% accurate. Here we have a typical instrument loop diagram for a pressure transmitter. This diagram shows us the complete wiring path, from the field device to the operator's control screen. Let's trace the signal, starting on the far left in the field. We have the pressure transmitter itself. Its two wires, white and black, run to a local junction box and connect to a terminal block. From the junction box, a main cable travels into the instrument local instrument room and enters the DCS marshalling cabinet. Here, the wires land on another set of terminals. Notice how the cable's overall screen, or shield, is terminated at the I's instrument clean earth bar. This is crucial for preventing signal noise. From the marshalling terminal, the signal goes to the DCS baseplate, which is where the I/O card's barrier is located. This single component both provides the 24-volt DC power to the transmitter and reads its 4 to 20 milliamp signal, which is why we call it a loop-powered instrument. This baseplate is connected by a prefabricated cable to the main controller card, which is slotted into the DCS system cabinet. Finally, the controller processes this information and sends the pressure reading to the DCS HMI, or Human Machine Interface, where the operator can monitor the process pressure. This loop diagram illustrates the complete wiring for two separate instrument loops, an input loop from a pressure transmitter and an output loop to a control valve. Let's trace the top loop first. Starting in the field, the pressure transmitter sends its signal. The wires run to a local junction box and then through a main cable into the instrument local instrument room. Here, the signal enters the DCS marshalling cabinet, where the cable shield is grounded at the IS earth bar. The signal then connects to the DCS baseplate, which interfaces with the controller in the DCS system cabinet. Finally, the controller processes this information and displays the pressure reading on the DCS HMI for the operator. Now, let's look at the bottom loop, which is an output. The flow is reversed. The operator sends a command from the DCS HMI. This command goes to the controller, which sends a signal out through its DCS. This signal travels through the marshalling cabinet and junction box, all the way back to the field to operate the UZ valve. This single diagram clearly shows the complete end-to-end wiring for both sensing a process variable and controlling a final element. This slide covers the most granular and important information on the diagram. This is where the drawing provides its real value to the installer and technician. First, terminal numbering. Every single termination point must have a unique, standardized number for easy identification. Next, shielding. Signal cables must be properly shielded to prevent electromagnetic interference and noise. The diagram must show exactly how this shield is terminated, which is typically at one end only. This leads to grounding. A robust grounding system is critical for both signal integrity and safety. The diagram specifies where instrument grounds are connected. We also specify cable cores, identifying the exact color or number for each wire. Finally, the diagram provides junction box and marshalling panel details, documenting the terminal block arrangement and I/O assignments. Creating the draft diagram is only half the job. The review and verification step is arguably even more important. A single error on one loop diagram can cause hours of delays and confusion during commissioning. To prevent this, we perform several rigorous cross-checks. First, we cross-check with the instrument index to ensure every instrument tag matches the master list and that all specifications are aligned. Second, we cross-check with the PNID to verify that the loop diagram accurately reflects the control strategy shown on the PNID. Third, we cross-check with the cable schedule to confirm that all cable tags, core assignments, and routing details are consistent. Finally, we use standard checklists to ensure no common details like grounding or shielding have been missed. This thorough review is crucial to ensure the design is error-free. To maintain consistency and professionalism across a large project, we always rely on standard templates and best practices. Every loop diagram is a formal engineering document. This starts with a standard title block. The title block contains essential information like the company logo, project details, drawing title, and sign-offs. Most importantly, it includes revision control. This is the system for tracking all changes. Every update must be documented, dated, and approved, so everyone is always working from the latest version. The template also includes space for drawing notes, which are general notes that apply to the drawing, and a drawing legend, which defines all the symbols and abbreviations used. Finally, it's good practice to list reference documents, such as the governing standards or procedures. Mistakes can happen. This slide highlights 3 of the most common and costly errors to avoid. First, incorrect polarity. For 2-wire loop-powered transmitters, wiring the positive and negative terminals backward will prevent the instrument from powering up. The loop diagram must make this polarity crystal clear. Second, tag mismatch. This is when the tag number on the loop diagram doesn't match the tag in the instrument index, on the P&ID, or on the physical device. This causes massive confusion during commissioning. Third, missing terminations. Forgetting to show how a cable shield is terminated or where spare cores are parked can lead to improper installation, signal noise, or safety hazards. How do we avoid these? By being vigilant and performing the rigorous cross-checks we just discussed. The loop diagram's job isn't done once construction starts. In many ways, it's just beginning. During commissioning, the loop diagram is the primary reference for the checkout team. As they perform loop checks, validating every wire from end to end, they may find small differences or make necessary changes. These changes are marked directly on the drawing in red pen, creating what we call red line updates. These red lines are then collected and used to create the final as-built drawings, which reflect the actual installed condition of the plant. The results of these checks are documented in loop check reports, which are part of the formal factory and site acceptance test documentation. After handover, the maintenance team relies on these accurate as-built diagrams for all future troubleshooting. This is why the loop diagram is a living document that must be maintained. In conclusion, loop diagrams are a truly vital tool in instrumentation design engineering. They are the definitive document that provides a comprehensive and standardized way to design, install, and commission every instrument loop in a plant. This presentation has covered the essential aspects of loop diagrams, from their purpose and key elements to the standards that guide them and the step-by-step process of creating them. By understanding these key elements, standards, and best practices, instrumentation engineers can create accurate and effective loop diagrams. These documents are the foundation for successful project delivery, a smooth commissioning phase, and safe, efficient plant maintenance for years to come. Thank you for your time. For further resources, be sure to refer to the industry standards we discussed and visit www.instrunexus.com for more instrumentation guides. If you enjoyed this video, please like, comment, and share it with a friend. Don't forget to subscribe and hit the bell so you never miss an update.